Hello everyone and welcome back. Today we're going to continue our exploration of optimization methods and discuss how we can actually optimize several variable functions using gradients. So let us assume we have the general problem where we seek to optimize the function f of x, where x is a vector containing variables say x1, x2, all the way down to xm. We already know that if this function only contains x1, we can use just single variable calculus. But if we have multiple variables, then we should be able to use multivariable calculus in order to optimize this. So we should already know that if we take the gradient of this particular function, for example, the gradient of f would be equal to, for example, a vector that contains, for example, the first partial derivative of f with respect to x1, the first partial derivative with respect to x2 of x, all the way down to the first partial derivative with respect to xn of x. This vector is always going to be pointing in the direction of the greatest change. So in particular, if we seek to optimize, in particular maximize the particular function, then if we take the gradient of this function at a particular point, then the gradient should be pointing towards the direction of the optimal solution. In particular, the critical point of this curve should be equal to, the top of the surface where the gradient is equal to 0, and then we can use, for example, the Hessian matrix to determine that that is indeed a maximum or possibly a minimum if we're trying to minimize things. Now, the downside with this optimization approach, in particular optimization with gradients, is that the constraints need to be empty. So therefore, this is an unconstrained optimization problem. We will introduce an alternative of gradient optimization that actually allows us to include some constraints in our problem. So to do a quick pedagogical example of how to use gradients to find the optimal value, let's assume that we're actually just going to be working with just some random function. Let's say the function is f of x1, x2 is equal to, say, x1 squared plus x1, x2 plus x2 squared plus 3, and our goal is to maximize this function such that the restrictions are null. So we have no restrictions, and it's a multivariable function, obviously a differentiable one. So we should be able to take the gradient of this function, set it equal to 0, find our critical points, and then classify those critical points as either a max or a min, and then find the global min of them or a global max of them if we have multiple critical points to analyze. All right. So if we take the gradient of this function, what do we need? So keep in mind the gradient of this function evaluated at x1, x2 is going to be equal to the partial derivative of f with respect to x1 of x1, x2 times the unit vector in the x1 direction plus the partial derivative with respect to x2 of x1, x2 times the vector in the direction of x2. Right? So we need to find the partial derivatives with respect to x1 and x2 first, and then plug them in. So if we take the partial derivative of f with respect to x1, that's going to give us what? So derivative of x1 squared, that's just going to be equal to 2 times x1. The derivative of x1 times x2, so x2 is just a constant, x1 is the variable, so that's just going to leave us with x2. x2 is a constant, and 3 is a constant as far as x1 is concerned. That means that is the partial derivative of f with respect to x1, and the partial derivative of f with respect to x2 similarly can be found to be equal to 2x2 plus x1. So these are our first order partial derivatives. Therefore, we want to find the point x1, x2 that makes both of these equations equal to 0. Because remember, if the gradient of f is equal to 0, that means the partial derivative of x1 of x is equal to 0, and the partial derivative of f with respect to x2 of x2, or x, is equal to 0 as well. So if we solve these equations set equal to 0, we're going to have the system 2x1 plus x2 is equal to 0, and x1 plus 2x2 is also going to be equal to 0 as well. If we represent this system as a system of linear equations, now keep in mind this system usually is not going to be a system of linear equations. By chance, we just happen to have a very nice system. So therefore, we can use just basic linear algebra to solve this. So we have the coefficient matrix 2, 1, 1, 2 times the unknown vector x1, x2, and that's going to be equal to 0, 0. So we should be able to see that the determinant of this matrix 2, 1, 1, 2 is going to be equal to 3, which is not equal to 0. Therefore, this equation, ax equals 0, has the trivial and only the trivial solution, in particular the 0 vector. That means the critical point, or the only critical point, is going to be the point x1, x2 is equal to 0, 0. Okay, now that we have the critical point, now we need to classify this as either a max, a min, or potentially even a saddle point. So the next thing that we need to do is construct what is called the Hessian matrix. So we need to take all of the second order partial derivatives and construct a matrix from it, take the determinant, and analyze. So the second partial derivative with respect to x1 twice can be found to be equal to 2. And the second partial derivative with respect to x2 twice can be found to be equal to 2. The partial derivative with respect to x1 and then x2 of x can be found to be 1. And the partial derivative f with respect to x2 and then x1 of x can also be found to be equal to 1. Once you have your second order partial derivatives, and keep in mind they don't have to be constants, they typically are functions of x1 and x2, one can find that the Hessian matrix of f evaluated at all points xy is actually just going to be equal to, so the x1 x1 partials first, then comes the x1 x2, then the x2 x1, and then the x2 x2. So that is the Hessian matrix, and notice it's a constant matrix at all points xy, which is actually pretty great. So we only have one critical point, 0, 0. So we need to find the determinant of the Hessian at that point. So we know the determinant of the Hessian, right? So the determinant of the Hessian matrix is just going to be equal to 2 times 2 minus 1 times 1. So that's going to be 4 minus 1, which is going to be equal to 3. And notice that's for all xy in the domain. Right? And I've just used x for x1 and y for x2, but hopefully you get the point still, even though I subtly changed the notations here. So that means the determinant evaluated at our critical point 0, 0 is also going to be 3 as well. All right? So let's analyze this situation, and let's see if we can figure out if this is a max or min. So since the gradient of f at the point 0, 0 is equal to 0, that means 0, 0 is a critical point. And the determinant of the Hessian matrix at 0, 0 is a positive number. That means what? So what does it mean for the gradient to be a positive, or the second derivative to be positive? So if we think back to example to the one-dimensional case, if we have this type of curve, clearly, we have that the gradient at the maximum and minimum point are both going to be equal to 0, but at minimums, the second derivative will be positive, and at maximums, the second derivative will be negative, right? So notice that we have a second derivative that is positive at the critical point. Therefore, we have that 0, 0 is a local minimum. In particular, it is the global minimum, and one should be able to show that via some other bounded calculus methods, but one can show that this is indeed a global minimum by showing, for example, that there is no other point that is actually less than this. And that algebra is actually not hard to show, but I'll leave that to you to verify. The next example that we're going to be using to demonstrate the use of gradients for optimizing multi-valued functionals would be this one. Suppose we have some line in, for example, two-dimensional space, x and y, that is represented by beta 0 plus beta 1x. Here, beta 0 and beta 1 are both constants to be determined. Let's assume that we have a data set of two-dimensional data, 3, 7, 4, 15, 5, 13, which is just a bunch of x comma y points. So what we want to do is find the values of beta 0 and beta 1 that minimizes this particular functional. This functional is sometimes referred to as the error sum of squares or the sum of squared residuals, and can be interpreted as follows. So what we're trying to do is, okay, we have a bunch of points sort of floating around in space, and what we need to do is find a line that best fits this data. This is the y hat line. So how do we define best fit? So these points should be as close to the line as possible, and those distances in green are known as the residual associated to that point. So as long as the sum of the squared residuals is close to 0, and ideally we want that to be as small as possible, then whatever values beta 0 and beta 1 that produces that minimization is usually what we refer to as the parameters of the line of best fit. Right? Some people usually call this the linear regression problem, and of course we can include other variables, for example, beta 1 x1, beta 2 x2, all the way down to say beta k xk if we really want to. All right, so we have our data points, and we want to find the equation of the line that best fits this data, assuming that we don't know any statistics or anything like that, right? Because for the two-dimensional case, there actually is some quick formulas, and actually for the multiple linear case, there is some formulas in terms of matrices, but let's pretend that we don't know them because there are problems that do not actually have closed forms, and we can actually approach them using the same exact method that we're going to talk about today. So what are we going to have? So let's actually write down our y hat values, right? So our y hat 1 values is going to be equal to beta 0 plus beta 1 times the first x value, and then y hat 2 is going to be equal to beta 0 plus beta 1 times our second x value. And then y hat 3 is going to be equal to beta 0 plus beta 1 times our next x value. So what I'm just doing here is I'm just inputting my 3, 4, 5 values from my data sets in here. And once I know my beta 0 and beta 1, that is going to give me my predicted values. And then I'm going to compare them to our exact obtained values, 7, 15, and 13, and see if the difference between them is close. If it's close, that means it's a great fit. So our functional that we're going to be minimizing is the functional f of beta, which is just going to be shorthand for f of beta 0, beta 1, and that's going to be equal to 7 minus the predicted value of 1, so that's going to be beta 0 minus 3 beta 1, the quantity squared, and then the next y value, which was 15, minus beta 0 minus 4 beta 1 squared, and then the last y value that we got was 13 minus beta 0 minus 5 beta 1, the quantity squared. So again, our goal is to minimize this function. So we need to take the gradient of this function and set it equal to 0. So the gradient of this function at, say, beta 0, beta 1 must be equal to 0. So this implies that the partial derivative of f with respect to beta 0 must be equal to 0, and the partial derivative of f with respect to beta 1 must be equal to 0 as well. So then we're going to have a 2x2 system of equations, solve it for beta 0 and beta 1, and that's going to give us our parameters for a line of best fit, and then we can find the sum of squared residuals associated to that minimization problem. All right, so let's see if we can actually write the general form for these equations, okay? So f of beta 0, beta 1, in the general form is just going to be equal to the sum from k is equal to 1 to n of yk minus beta 0 minus beta 1 xk, the quantity squared. For our problem, it's going to be n is equal to 3, and we can input our yk's and xk's if we want. But taking the derivative in this form is actually a lot easier. So the first thing I'm going to do is take the derivative of f with respect to beta 0. So notice the derivative of sum is just going to be the sum of the derivatives, and the derivative of something squared is just going to be 2 times something. And I'm going to factor out the 2 out of the sum. So we have 2 times the sum from k is equal to 1 to n of, so 2 times something, so 2 times something, minus the derivative of that interior, right? So we're taking the derivative with respect to beta 0, which means yk is a constant, that goes to 0, beta 1 xk also a constant, that goes to 0, and we're just left with the negative 1 in front of the beta 0, so I'm just going to put that at the end, and we're going to be setting this equal to 0. So our first equation is going to be the sum from k is equal to m of yk minus beta 0 minus beta 1 xk is equal to 0. So that's the first equation for our system that we need to solve. Now I'm going to take the derivative with respect to beta 1. So the partial derivative with respect to beta 1 is going to be equal to what? So we're still going to have a 2 times the sum from k is equal to n of the inside right? Now, what is the derivative of the inside with respect to beta 1? So that's a constant, that goes to 0, that's a constant, that goes to 0, and we have this minus xk next to the beta 1, so we need to be multiplying by that. So minus xk is equal to 0. So notice that we have a constant there, we have that minus 1, we can divide by minus 2, and that's going to give us still 0. So that means the second equation that we have is going to be the sum from k is equal to 1 to n of, we can distribute that xk in if we want to. So we're going to have xk yk minus beta 0 xk minus beta 1 xk squared is equal to 0. Okay, so that gives us that particular equation, and now we need to input our data points xk, yk, where k ranges from 1 to 3, and then construct our system. So let's just recall what our set of data points was. So our set of data points was 3, 7, 4, 15, and 5, 13. So if we input these into those equations and combine like terms, we're going to have the following system. 3 beta 0 plus 12 beta 1 is equal to positive 35, and 12 beta 0 plus 50 beta 1 is equal to positive 146. So that's, of course, a linear system, which is very, very nice. So we can write this in matrix form as 3, 12, 12, and 50 times our unknown values, beta 0 and beta 1, and that's going to be equal to 35 and 146. So what is the determinant of this coefficient matrix? So the determinant, let's actually call that matrix A just for short. So the determinant of A is going to be equal to 50 times 3 is going to be 150 minus 12 times 12, that's going to be 144 with a determinant of 6. And that means that the inverse of that matrix A is going to be equal to what? So we're going to be dividing by 6 leadingly. We're going to swap our primary entries and negate the other two. Right, that's our shortcut formula for the inverse. So that means we can solve this equation, A beta is equal to B, by multiplying both sides on the left by the inverse. So beta is going to be equal to A inverse times B. So that means beta 0, beta 1, is going to be equal to 1/6 of the product of 50 minus 12 minus 12, 3, and the vector 35, 146. And one can find that the product of those two matrices is going to come out to 2 minus 18. And then we can factor that 1/6 in, and we're going to have 1/3 and minus 3. Right? And that gives us our solution. Actually, just a quick misprint. That should be minus 2 and positive 18, and switching those signs around in that solution. So minus m plus 3. All right. So once we have that, that gives us our solution for our line of best fit. That means our line of best fit is given by y hat is equal to our vertical intercept, negative 1/3, plus 3x. Right? And that pretty much is how you do, for example, two-dimensional linear regression. Now I'm just going to state the formula where you actually can use formulas to quickly do this without doing any gradients, just in case you aren't aware of it. So what we're going to do is we're going to define the standard deviation of x to be equal to the sum of our xk minus the averages of our x's divided by m minus 1. The standard deviation of y is a similar formula, yk minus y bar, the quantity squared, divided by m minus 1. The covariance of a data set can be found by doing the sum of the products of xk minus x bar times yk minus y bar, all divided by m minus 1, and the correlation coefficient can be found doing the covariance of s divided by sx, sy. So if you want to perform this linear regression problem without doing any calculus, then for a data set in R2, then the coefficients for that linear regression model are as follows. Beta 1 can be found by doing r times sy divided by sx, and beta 0 can be found by doing y bar minus beta 1 times x bar. Okay, and those are the closed form representations for the linear regression parameters, but that's just a very special example where you can actually use gradient for minimization of non-linear problems. So I hope you enjoyed, and I'll see you in the next video where we take a look at a numerical technique that can be used to approximate anything without technically not knowing calculus, as long as you know some approximation methods for derivatives. So I hope to see you there. Take care.